if you guessed that the first pour was ice cold and the second pour was boiling hot. Congratulations. Your brain just performed a highly advanced acoustic calculation without you even noticing. But here's the really weird part. You didn't need to see the steam rising from the kettle to know that. You didn't need to see ice cubes floating in the pitcher. You just knew, and you aren't alone. In 2013, researchers conducted a series of empirical studies and discovered something genuinely mind-blowing. If you sit a group of random humans down, blindfold them, and play recordings of hot and cold water being poured, they can distinguish the temperature with an astonishing 95 to 99% accuracy. It is an implicit, near-perfect biological superpower that you use every single day. But how? From a distance, hot and cold water look absolutely identical. They are made of the exact same molecules, and yet when they hit a cup, they speak entirely different languages. Today, we are going to crack open the physics of a simple splash and find out how your ears can detect heat. For years, science communicators and casual physics fans had a very simple, elegant explanation for this mystery. They blamed it on viscosity. Viscosity, in simple terms, is just how thick or sticky a liquid is. At a cool room temperature of 20 degrees Celsius, water has a viscosity of roughly 1.0 centipoise, or Cp. It flows normally, but when you heat that water up to 99 degrees Celsius, right near the boiling point, something drastic happens. The thermal energy tears apart the weak hydrogen bonds holding the liquid together. The water molecules become highly energetic, making it incredibly difficult for them to join together or stick to one another. As a result, boiling water becomes nearly 4 times less viscous, dropping to about 0.2 Cp. To put that in perspective, boiling water is physically closer to the thickness of a light, runny cooking oil than it is to room temperature water. So, the classic theory goes, hot water sounds different because it is thinner. It splashes faster, flows easier, and that makes a different pitch. It sounds perfectly logical, except there's a massive catch. Viscosity changes how water flows, how it spills, and how it coats a container. But viscosity itself doesn't actually vibrate the air. Viscosity cannot travel through space to strike your eardrum. To hear a sound, something physical has to actively compress the air and create sound waves. So if the thickness of the water isn't what we are actually hearing, what is? In 2024, a team of physicists published a groundbreaking study that finally settled the debate. They used high-speed photography and highly sensitive acoustic sensors to analyze exactly what happens when water is poured. And they discovered that when you listen to water pouring, you aren't actually listening to the water at all. You are listening to the sound of underwater air bubbles. Every time a column of liquid hits a surface, it drags pockets of air down into the pool below. Once trapped underwater, these pockets of air don't just sit there. They are highly elastic, and they begin to compress, expand, and vibrate like microscopic springs. Back in 1933, a Belgian physicist named Marcel Minnaert calculated the exact physics of these vibrating underwater bubbles. He discovered that an underwater bubble acts like a miniature acoustic loudspeaker, and the pitch of that speaker, its resonant frequency, is governed by a beautifully simple rule. The frequency is inversely proportional to the bubble's radius. In plain English, big bubbles produce a low-pitched, rumbly bass. Small bubbles produce a high-pitched, grade-abraded, crisp treble. Now let's tie this back to temperature. Remember how we said hot water is 4 times thinner and has much lower surface tension? Because hot water has such weak surface tension, the pouring stream cannot hold itself together. It breaks apart into a chaotic machine gun of individual droplets before it even hits your mug. When this unstable, turbulent stream smashes into the cup, it drags massive, irregular pockets of air down with it because hot water is so thin. It lacks the cohesive strength to shear those large air pockets into smaller pieces. So they stay big. The result? Hot water is filled with an abundance of giant vibrating bubbles. And via minor resonance, these giant bubbles vibrate slowly, producing that signature, heavy, low-frequency rumble. Cold water, on the other hand, is a master of self-control. Its high surface tension acts like a tight elastic skin, holding the pouring stream together in a cohesive, solid rod of liquid. It enters the glass smoothly, dragging very little air down with it. And the small amount of air that does get trapped is immediately ripped apart by the thick, viscous shear forces of the cold water, shredding them into tiny, uniform spheres. Small bubbles mean a tiny radius. A tiny radius means an incredibly high frequency. So when you hear cold water, you are listening to a symphony of thousands of tiny, high-pitched, microscopic speakers. When you hear hot water, you are listening to a few giant, low-pitched subwoofers, but the physics doesn't stop underwater. There is another, more subtle layer to this acoustic puzzle, and it has to do with the container itself. The empty space inside your mug acts exactly like the body of an acoustic guitar. It's a resonating chamber, also known as a Helmholtz resonator. When bubbles vibrate the water, those sound waves bounce around inside the empty air column of the cup before escaping to your ears. But as you pour steaming hot water, it heats the air inside the cup. And in the world of physics, temperature dictates the speed of sound. In normal room temperature air, sound travels at about 343 meters per second. But at 80 degrees, the temperature of hot tea, the air molecules are highly energized, allowing sound waves to rocket through the air at nearly 380 meters per second. Because the speed of sound has changed, the resonance properties of the air cavity shift dramatically. It alters the timbre of the pouring sound, making it feel more open, hollow, and rumbly compared to a cold cup. So, not only are the underwater speakers playing a deeper bass line, but the acoustic speaker cabinet itself has just been remodeled by the heat. Which brings us to the final, most beautiful part of this entire story. You. How did you learn to decode this incredibly complex physics equation? You aren't born with a textbook on fluid dynamics in your head. You don't consciously calculate bubble radius or speed of sound variations. Your brain learned this through a process called statistical learning. From the day you were born, you have watched and listened to people pouring liquids. Data. Every time you made hot cocoa, poured a glass of juice, or filled a bath, your brain was quietly logging data in the background. It noticed that high-pitched, crisp sounds always correlated with cold sensations. It noticed that low-pitched, rumbly, hollow sounds always correlated with steam and heat. Over millions of repetitions, your brain mapped these acoustic frequencies directly to thermal temperatures. You built a predictive model of the physical world, so precise that you can determine the atomic movement of water molecules using nothing but a pair of biological ears. So, the next time you hear a kettle boil or listen to someone pour you a cold drink from across the room, take a second to listen closely. Your brain has already read the temperature of the room before you've even taken a single sip, because in the end, hot and cold water don't just look different. They sound like different worlds.